Is 0 a natural number? We can all agree that the numbers we use for counting, so 1, 2, 3, 4, and so on, are the natural numbers. But 0? Well, it depends on who you ask and what purposes you use for the naturals. Perhaps you have the harmonic series, which you may want to describe as the infinite sum of 1 over n for all natural n. Perhaps you're a computer scientist or a programmer, in which case your counting starts at 0. Well, in the end, it's really just semantics, and it doesn't cause much concern for most of mathematicians as long as you're clear on its definition. But the question, is 0 a natural number, holds an even more difficult question. What is a natural number? I mean, okay, let's include 0 and say 0, 1, 2, 3, and so on, but what does so on mean? Oh, okay, it goes to infinity. Well, what does that mean, formally? Remember, we're doing mathematics, so we need a formal definition and construction of what the natural numbers are. And then we have, well, the integers and the rationals. How do we define them? And then the reals? That one is especially difficult. Where do you even start? Well, as it is with most of mathematics, we start with some assumptions. Our goal is to begin with the assumption that 0 exists. Specifically, that it is something that we call a set. And we will see that from this simple assumption, along with a couple of other assumptions, we can create infinity. So what are sets? Well, intuitively, we want them to be collections of mathematical objects. But of course, we want to formalize what sets are using some assumptions, also called axioms about sets. There are many different axioms of set theory, but here are some elementary ones which will give us a foundational idea of what they are. Two sets are equal if they have the same elements. There exists the empty set. There exists a set containing two already existing sets. The union of sets is a set. The collection of all subsets of a set is a set. And a definable subcollection of a set is a set. Now, if you watched my axiom of choice video, you may notice that these are not all of the axioms of what is called ZFC, the most commonly used system of axioms for set theory. Instead, they are some of the earlier axioms which later then developed into ZFC. But for now, they alone allow us to form some really nice foundational concepts. The reason we do this is to use just the necessary axioms to formalize the sets of naturals, integers, rationals, and the reals. Can we describe these sets using just these axioms of set theory? Well, let's start simple. For 0, we can use the axiom of the empty set and denote the empty set as 0. Now, how about the numbers after, like 1, 2, 3, and so on? To define these numbers, let's introduce a new concept called the successor set. Take any set, A, then the successor set of A, denoted A+, is the union of A and the set containing A. Now, let's make sure that this is a set by our axioms. The set containing A is a set by the pairing axiom, since we can pair A with itself and just get the set containing A. Then A union the set containing A is a set by the union axiom. So, nice. Our successor set is actually a set. Then define 1 to be the successor set of 0, which is just the empty set, then 2 to be the successor of 1, then 3 the successor of 2, and so on. In general, let n plus 1 be the successor set of n. Now, this definition of the natural numbers is not some God-given formalization that we must use. We can, if we want, formalize them in some other way. But this definition does have a lot of useful properties. For one, the ordering of the naturals is trivially easy to describe. You can see that 0 is an element of the set 1. Then 1 and 0 are both elements of 2, then 0, 1, 2 are elements of 3, and so on. So we can say a natural n is less than m if and only if n is an element of m. then you can prove, which we won't do here for the sake of time, that this definition of the order satisfies all the properties you'd expect for the naturals. And this definition gives a nice description of a natural number. A natural number n is the set of all the natural numbers that come before it. But of course, this is not a formal definition. So how do we formally define what a natural number is? And furthermore, how can we formally define the set of all natural numbers? Well, here we run into a problem. You see, the axioms we have so far are great at capturing the idea of finite sets, but when we get infinitely large, well, we get stuck. No amount of unioning, pair setting, and power setting will turn a finite set into an infinite one. Now, we can just give up and say that, you know what? Sets should just be finite objects. But for most mathematicians, we say infinity should exist, and that sets should be able to describe them. So we want sets to be infinite. But how do you write an axiom for that? There is an infinite set. Well, that sounds simple enough, but that's too vague, and it's not like we formally described infinity. So to formalize infinity, we use a concept that for some of you may be quite familiar: induction. Induction is a proof technique, which allows us to easily prove an infinite number of statements at once. It's pretty straightforward, so I'll explain with an example. Suppose we want to prove that for any natural number n is less than 2 to the n. Now, instead of checking each n value and making sure it satisfies this fact, we do this. First, take a base case. This is usually the statement, but for a specific n value, usually 0 or 1. For example, we know for n equals 0, 0 is less than 2 to the 0, which is 1. Next, we do something called the induction step, where we suppose that the statement is true for some value n equals k. This assumption is called the induction hypothesis. Then we try to prove that assuming this induction hypothesis, the statement is also true for k plus 1. With our example, if we assume k is less than 2 to the k, then k plus 1 is less than 2 to the k plus 1. Then notice that 1 is less than or equal to 2 to the k for any natural number k. So 2 to the k plus 1 is less than or equal to 2 to the k plus 2 to the k. And so k plus 1 is less than 2 to the k plus 2 to the k, but this is just 2 to the k plus 1. So now we showed the induction hypothesis. But look, we already proved the case for n equals 0. But according to our induction hypothesis, if the statement holds for 0, then it also holds for 1. But then if it holds for 1, then it should also hold for 2, and then 3, and 4, and 5, and so on for infinity. In fact, it should hold for any natural number. So proof by induction is a powerful tool which allows us to prove an infinite number of things in a finite number of steps. And this is the exact idea that we'll use to build our infinite set. First, as an analogy to our base case, we suppose that this infinite set, whatever it may be, must contain 0. Again, it's the empty set. Then, like the induction step, we say that for any set that is an element of this set, its successor must also be in this set. Now, clearly then, this set must be infinite. I mean, 0 is in this set, but that means the successor of 0, 1, is in this set. Then the successor of 1, 2 is in this set, then 3 and 4, and so on. By just these two rules, we have a set that contains at least what should be all of the natural numbers. Let's call any set that follows these two rules an inductive set. But is this collection actually a set? Well, that's what the axiom of infinity asserts. It says that there exists an inductive set. By our intuition and its very definition, this set is infinitely large, and we can formally describe it using first-order logic. There's no wishy-washiness about what an inductive set is. Now, clearly, by construction, every inductive set contains all the naturals, or more specifically, they contain everything that we want to call the naturals. But it can contain more. Remember, the successor operation works on any set, not just the numbers, and there's nothing stopping an inductive set from containing some other random stuff and their infinite sequences of successors. But again, we know that every inductive set must contain at least the naturals. So with this in mind, we can precisely define the natural numbers, the intersection of all inductive sets. Another equivalent way to define the naturals is the smallest inductive set. In any case, the set of natural numbers looks exactly as we expect, 0, 1, 2, 3, and so on. But now we have a precise, formal way of constructing and describing this set. Then finally, we can define a natural number as any element of the set of naturals. So by the axiom of infinity, we have constructed our first infinite set, the naturals, but we've only just begun. First, we have operations we want to define, namely addition and multiplication. For the sake of brevity, we'll only mention the general idea of operations within these number systems since they can get quite repetitive. Just like how we defined an inductive set, we'd like to define addition and multiplication recursively. What does this mean? Well, you can imagine addition and multiplication as functions, which take two inputs and give an output. Now, obviously, we can't list out all the possible values for addition and multiplication to define these functions. So instead, we use recursion, where the function we're defining is applied in its own definition. For example, let's take addition. Call our addition function a and define a of m0 to be m for any natural number m. Then instead of trying to define a of mn for any two naturals m and n, we instead define a of m and the successor of n as the successor of a of mn. Now, this might look confusing, but we can see that this defines the function a for all values. A of m1 is, by definition, the successor of a of m0, which is the successor of m. Then a of m2 is the successor of a of m1, and so is the successor of the successor of m, and so on. Now, if we want, we can use our usual notation for addition, and well, it looks very familiar. The reason we write this as a function is because we can formally describe these as sets, and so all the operations make sense in set theory. Then we can use addition we define to recursively define the multiplication function by m of m0 equals 0, and then m of m, the successor of n, as m of mn plus m. Again, rewriting in our usual notation and the definition becomes clear. Then you can go on to prove stuff like associativity and commutativity to show that indeed these operations are exactly what we want for the naturals. Now, just one note. The ability to define functions on the naturals recursively like this is something that we cannot take for granted, and thus must prove using set theory. It's a very powerful tool, and showing that these functions exist is itself a deep theorem which we cannot unfortunately get to today. But the point is, you can construct these operations in set theory. Now, let's construct the integers. Remember, all we have to work with right now are the naturals. So how do you represent negative numbers with just positive numbers and 0? Well, first, let's look at a tool we have, ordered pairs. Sets on their own are unordered, so 1, 2 and 2, 1 are the same set. It turns out, however, that we can define ordered collections of elements using just sets. In other words, ordered pairs and tuples are themselves sets. If you want a formal construction of this, I've explained it in my axiom of choice video, but for now, let's assume that you can safely use ordered pairs and tuples to build the integers. So how? Well, here's the intuition. You're hopefully familiar with the notion of subtraction. Take two natural numbers, a and b, and then a minus b can represent a negative number. For example, minus 2 can be represented by 0 minus 2. So the idea is to use pairs of natural numbers to represent a negative number. But since we want to define everything formally, let's take this intuition carefully, step by step. First, a minus b and b minus a can be different, so we want to use ordered pairs instead of just unordered sets. So let's just associate the term a minus b with the ordered pair a comma b. Now it's important to note that we're not formally using subtraction anywhere. Instead, we're borrowing its intuition to build something that feels and looks like how we want the integers to function. But we're still not really done because, well, different ordered pairs could represent the same integer. For example, 0, 1 represents -1, but so does 1, 2, or 2, 3, or in general, n plus 1 for any integer. We definitely don't want this. We want exactly one set to describe one integer. No more, no less. Is there a way we can, in a sense, describe the sameness of 0, 1, 1, 2, 2, 3, and what they represent? Maybe we can have a set which contains all the different ordered pairs that can represent the same integer, and then that set could be defined as that integer. Well, the formal notion behind this idea is called the equivalence class, but to use this tool, we need to talk about relations. Take any set X. Suppose we wanted to compare the elements of X in some interesting way. More specifically, we can pick any two elements of X in some order and define some relation such that we can either say these two elements are related or they're not related. For example, let X be the set of naturals and consider the less than relation. Let's take an ordered pair of natural numbers, for example 2, 4, then since 2 is less than 4, we can say that 2, 4 satisfies the relation. On the other hand, 5, 3 does not satisfy the relation. Note that the order here matters since 3, 5 does satisfy the relation. Now, take all the ordered pairs which do satisfy a relation and put it into one set. Then let us formally declare that this set is the less than relation. Again, in set theory, we try to code everything in terms of sets, so it may feel weird that a relation is a set, but it works, since this set contains exactly the information we need to know what this relation does. Since we're comparing two elements, this kind of relation is called a binary relation. Also note that this relation is a subset of the set of all ordered pairs of the naturals, which we denote n times n, or n squared. Conversely, any subset of n times n defines its own unique binary relation on the naturals. Now, some relations have properties that are easy to work with. For the less than relation, we can see that order matters, or that elements are not related to themselves. But some relations don't have these restrictions. When order doesn't matter, so if x is related to y, then y is related to x, a relation is called symmetric. A relation where all elements are related to itself is called reflexive. Finally, one nice property of the less than relation is that if x is related to y and y is related to z, then x is related to z. This property of relations is called transitivity. Relations that are reflexive, symmetric, and transitive are really nice to work with, so they have a special name: equivalence relations. Why is this so important? Well, these three rules of an equivalence relation are strict enough that they can cleanly divide up a set into groups based on this relation. Basically, we have a bunch of disjoint subsets where elements are only related to those in their own subset. These different subsets are called equivalence classes. Then here's a really nice part. You may wonder how we can denote each equivalence class. Well, you just choose any element in each subset. Then this set of all elements in X related to this representative is exactly the equivalence class. So choose your favorite representative. We'll later see that this act of choosing any representative won't have issues when we start defining operations. So why do we want equivalence classes? Well, they basically allow us to group elements of a set by some relation, and do so in a nice, clean manner. And this is exactly what we want with the integers. We have a bunch of different ways to denote an integer using ordered pairs, but if we could define some equivalence relation, we can group all these ordered pairs describing the same integer into one equivalence class, and then that equivalence class could be our integer. So then what will this equivalence relation look like? Well, we want a comma b to be related to c comma d if a minus b and c minus d are the same integer. That is, a minus b equals c minus d. But remember, we're working with the tools we have for the naturals, and we haven't defined subtraction yet. But we have defined addition. So we define our relation as ab is related to cd if and only if a plus d equals b plus c. You can easily check that this relation is an equivalence relation over n times n. Then finally, formally. Define an integer as an equivalence class defined by this equivalence relation. For example, -1 is formally the equivalence class represented by 0, 1, which is the set containing 0, 1, 1, 2, 2, 3, and so on. Again, it's important to note that this relation is over the pairs of naturals n times n, or simply n squared. So, as weird as this looks, this relation is formally a subset of n squared times n squared, and any equivalence class is a subset of n squared. Now, we denote the set of all equivalence classes of n squared over our relation R as n squared over R. Then this right here is what we define as a set of all integers. Not exactly what you're expecting, huh? But this is a set using our axioms. Remember, by the axiom of comprehension, any definable subset of a set is a set. So each equivalence class AB of R is just a subset of n squared, defined by CD in n squared such that A plus D is B plus C. Then since n squared over R is just a set of subsets of n squared, it is a subset of the power set of n squared. More specifically, the set of elements in the power set of n squared, such that X is some equivalence class AB of R. So this set of integers is a set. If you're a bit lost on why we have to make things so complicated when building these new sets, think of it this way. We know what the integers feel like. It goes on to infinity on one side of 0, and it goes to infinity to the other side of 0. And we are able to add and subtract and multiply, and there's a nice ordering and all that. Now, we want a set that basically has these exact properties. Nothing more, nothing less. Now, the difficulty is that we're limited on exactly how we can build these sets, since we try as much as possible to limit our set of axioms. So we have to think of some clever ways to construct a set that share the same properties as the integers. And this equivalence class construction of the integers is exactly that. Moreover, the nice thing about our construction is that the operations and the ordering are very easy to define. After all, the integers are built from the naturals, so we can easily define addition and multiplication by just borrowing from the addition and multiplication in the naturals. Specifically, we have that a minus b plus c minus d is a plus c minus b plus d, and a minus b times c minus d is ac plus bd minus ad plus bc. We can then easily write this in terms of our equivalence classes. Now, one thing. How do we know that our operations don't change if we choose different representatives for each integer? Well, because of how we defined our equivalence relation and how we defined addition and multiplication, it's easy to show that this problem does not happen, or as we like to say, the operation is well defined. We can also prove the existence of additive inverses, which gives us subtraction. And finally, we can show ordering on the integers by again borrowing the ordering of the naturals. All this to say, because we carefully designed our set using the naturals, the important mechanisms of the integers can be easily derived. Now that we have the integers, the rationals aren't too difficult to construct. It's very similar to the construction of the integers, so we'll go a bit faster. Again, let's borrow some intuition on what we feel like the rationals should look like. When is a rational a over b equal to a rational c over d? Well, when ad equals bc. So, just like the integers, why don't we define an equivalence relation? This time, let's denote E over the set of pair of integers, where the fraction a over b corresponds to the pair of integers a comma b. One note is that we don't want to divide by 0, so we restrict this set of pairs so that 0 cannot be in the second entry. Let's call this set F for fractions. Now for our equivalence relation over F, we just say AB is related to CD if and only if AD is equal to BC. It's then not very difficult to show that this relation satisfies the three equivalence relation properties of reflexivity, symmetry, and transitivity. Then finally, we define the set of rationals as the set of E equivalence classes over the set F. Now, how do we define operations like addition and multiplication? Well, a over b plus c over d is ad plus bc over bd, and a over b times c over d is ac over bd. We can easily write this in terms of our equivalence classes using our previously defined integer operations. and as before, it turns out these operations are well defined. Similarly, multiplicative inverses and ordering are not too difficult by, again, just borrowing the operations and ordering of the integers. One final and interesting thing to note is that with our definition, technically the naturals are not a subset of the integers, and the integers are not a subset of the rationals. Why? Well, we formally define the integers as equivalence classes of pairs of naturals, but the natural numbers are not those things. Similarly, the rationals are equivalence classes of pairs of integers, so our formal construction of an integer is also not a rational. This is one disadvantage of our construction, but it's not too big of a problem. We can easily associate each natural number in n with an integer in z by relating n in n with n, 0 in z. And similarly, we can associate each z in z with z, 1 in q. So for all intents and purposes, this formal inconvenience isn't too important, but as it may sometimes be with mathematics, not everything is perfect. But now, we go to the big one, the real numbers. I think for the integers and the rationals, you can kind of see how to define them. I mean, even without all this set theory formality, you can use some basic notation to at least describe what these sets should look like. But the reals? Where do you even start? As we've shown before on this channel, the real numbers are literally bigger in size to the naturals, the integers, and the rationals. Well, like before, let's look at what the defining properties of the real numbers are. Like the other sets, but even more so here, we're not really finding a set that is literally the real numbers. Instead, we are declaring what the real numbers should be on our own. We say that the real numbers are a set that fulfill some number of properties, and then we find a set that fulfills those exact properties. Again, we kind of know what the real numbers should look like, but to actually formally define what it should be requires input and choice on our part. So what should the real numbers satisfy? Well, first, we have to have the operations of addition, multiplication, subtraction, division with the properties as we know, commutativity, associativity, and so on. We also want a nice ordering, and the formal requirements for this ordering is called a total ordering, where the ordering is reflexive, antisymmetric, transitive, and total. Addition and multiplication should also be compatible with this ordering. All of this is pretty straightforward and basically a formal restatement of things that most of you have seen in some capacity. So we won't go too deep into this stuff since we have one other important property that separates the reals from all the other sets we've constructed so far. That property is called the completeness of the reals. The intuition of this property is that the real numbers have no gaps. If you think about the rationals, they are infinitely dense, as in between any two rationals you can find another rational number. But there are still gaps in the rational number line. What do I mean by this? Well, consider the set of all rationals that satisfy q squared is less than 2, or equivalently, q is less than square root of 2. Now, is there a smallest rational that is bigger than all of the elements of this set? You can imagine that this set is a certain range within the number line, and we want a unique, smallest rational number that bounds this range. For this reason, such a number is called the least upper bound. For example, by how we define this set, it's pretty easy to see that the least upper bound is the irrational number square root of 2. But that's not a rational, and that's because there is no rational least upper bound. To show this, suppose b is a rational upper bound. Since it's rational, we can write it in its decimal expansion. Now, intuitively, we know that this rational upper bound must be greater than the square root of 2. So here are the digits of square root of 2. Then we can use these digits to write a new upper bound b prime by just finding the first digit of which b is greater than square root of 2, which must always exist as b is rational. Then b prime is less than our original upper bound, and so in other words, for each rational upper bound of the set, we can always find a smaller rational upper bound. This isn't a formal proof or anything, but hopefully it gives intuition on what we mean by gaps. We want a set which can assign a number to these least upper bounds, and the rationals just can't. There are holes in the rational number line in which these least upper bounds should go. Now a set, with an ordering in which this property holds. That is, for any subset which has some upper bound, there is a least upper bound is called complete. And this is the exact property that we want the reals to satisfy. In fact, in a sense, we can call any set that fulfills this completeness property along with the operations and the ordering working as usual as the real numbers. Just like vector spaces or groups or sets have axioms that define that structure, we can have these properties as the axioms that define the real numbers. So again, we're not discovering the God-given construction of the reals. We're just finding a set which we can construct that satisfies these properties and is nice to work with. And there are a lot of ways to do this, but we're going to use something called Dedekind cuts, and it relates to what we just did. Recall the set of rationals that are less than the square root of 2. What if we just denote this set as the number square root of 2? Now obviously we can't exactly define it this way since we can't define a real number using a real number, but this is the sort of intuition we're building on. We want to define a real number as a set of all rationals less than it. Perhaps it's easier to construct this the other way. We want a set of rationals A, which is less than some value, so it should satisfy some clear properties. First, there shouldn't be some lower bound since we want all the rationals less than some value. We formally denote this by saying that for any x less than y in the rationals, if y is in this set, then so is x. This property is called downward closed. Second, it can't have some greatest element since we want a set which is defined by having all elements less than some value, and having a greatest element would imply that there is nothing between this greatest element and this value, which contradicts the denseness of the rationals. Finally, this set can't just be the empty set or all of the rationals. This is just to remove some trivial cases of our other two properties. If a subset of rationals fulfills these three criteria, then it is called a Dedekind cut. To put intuition behind the formality, we're basically cutting the number line at some point, and all the rationals on this half of the real number line forms a Dedekind cut, which corresponds to the real number we cut at. Then we can formally define the set of real numbers as the set of all Dedekind cuts, which is definable as a subset of the power set of the rationals. And look, this definition takes a bit of thinking to wrap your head around and it's super theoretical, but the point is that we can basically fill all the gaps between the rationals, which are just their irrational numbers, by associating that gap with all the rationals less than it. Furthermore, we can also define each rational with a Dedekind cut. Specifically, a rational number q is associated in our real number construction to the Dedekind cut containing all the rationals less than q. Of course, again, by this construction, the rationals are not formally a subset of the reals, but this isn't too important since every rational can be naturally corresponded to a unique Dedekind cut. Let's quickly look at the ordering and the operations. For the ordering, how should we define alpha is less than or equal to beta for any two real numbers, alpha and beta? Well, intuitively, if alpha is less than or equal to beta, then the Dedekind cut associated with beta contains the Dedekind cut associated with alpha, just by the very definition of these sets. So the ordering in the reals is simply just a subset relation. Then you can easily prove that this subset relation does indeed satisfy the properties of a total ordering. For addition, we define them this way. There's a bit of work to be done, like proving that these sets are actually real numbers, that is Dedekind cuts, and that they satisfy the desired properties. Additive inverses and multiplication are a bit more complex with some more subtle intuition, but you can also show that these definitions fulfill the properties we need. And I'd love to dive into the formal proofs on why these definitions work, but honestly, it's a lot of tedious work, which requires a lot more set theory, and I feel it isn't relevant enough to dive into today. But the important thing is, this construction fulfills the necessary properties of real numbers regarding ordering and operations. Finally, we can show that this set is complete with respect to our ordering. As a reminder, this means every subset of R with an upper bound has a least upper bound. Here's the idea. Suppose you had a subset S of the real numbers with some upper bound U. We want to show that there exists a least upper bound U prime. Now we have our total ordering defined by the subset relation, so by definition, an upper bound U of this set S satisfies alpha is a subset of U for all alpha in S. Now look at this. If alpha 1 and alpha 2 are both in S, then alpha 1 and alpha 2 are both subsets of U. Then alpha 1 union alpha 2 is also a subset of U. Similarly, if alpha 3 is in S, it is a subset of U, so alpha 1 union alpha 2 union alpha 3 is a subset of U. Now, what if we keep doing this and union every element of the set S? Let's denote this union like this and call this the union set of S. Then again, the union set of S is a subset of U. And remember, U is any upper bound of S, so this means that the union set of S is a subset of any upper bound, U. But it turns out that the union set of S is a Dedekind cut. I highly recommend you to try and show that this set does fulfill the three properties of a Dedekind cut, that it's not empty nor all of the rationals, it's not more closed, and it doesn't have a greatest element. As a hint, use the fact that for any element P in the union set of S, there exists an element alpha in S such that P is in alpha. Since the union set of S is a Dedekind cut, it is a real number by our construction. But look, clearly every element of S is a subset of the union set of S, just by what a union set is. So the union set of S is an upper bound of S. But we also showed that the union set of S is a subset of any upper bound U of S. So by definition, the union set of S is the least upper bound of S. Thus, R is complete. So, we're done. We constructed the naturals, the integers, the rationals, the reals, and the respective operations and orders, all within set theory. The reason we do this is to show that we can do all of mathematics within this logical system of our axioms of set theory. Once we know that there is some formality to what we're doing, that the very numbers and the sets that we use aren't just there because we feel like they should be, but that we can actually construct them with a set of axioms which we can observe and apply and study, hopefully everything feels a bit more stable. You see, set theory isn't some painstaking formalization for the sake of formalization. Set theory gives us the framework and the foundation upon which we can work. And the axioms, theorems, and tools from set theory have incredible applications in every branch of mathematics you can think of. Until next time.